Let's consider a planet orbiting a star at the origin, and with an orbit given by this ellipse, which is RT equals R1 cosine omega t, R2 sine omega t, and 0. And R1, R2, and omega are positive real numbers. So let's let A of t tilde be the area swept out by the position vector RT from t equals 0 to t equals t tilde. So what does this A of t tilde mean graphically? So if this is my universe and this is my star at the origin, my planet traces out this ellipse. And A of t tilde is just going to be, so this is my R of t 0. This is my R of t tilde. My A of t tilde is just going to be this area, which is swept out by my position vector of the planet. I want to investigate the rate of change. I want to find the rate of change of my area with time. So how do I do this? In order to find the rate of change of the area, I just need to see how much does A, my area, increase as my t increases a little bit. So graphically, so if this is my R of t, and this is my R of t plus dt, where dt is a small increase in t, I just want to find the increase in area, which is this. And notice that my area is basically a triangle. So increase in A is approximately a triangle when my increase in t is small. So when dt is small. And how do I calculate the area of such a triangle? So suppose this is my triangle. Then the area is twice the area of the parallelogram formed by just piecing another half of this triangle. And therefore, the area of my triangle is just half of the area of my parallelogram. But I know how to compute the area of my parallelogram because it's just going to be the size of the cross product of my two vectors. So it's just going to be the size of this vector cross this vector. And so area of triangle equals 1/2 of area of parallelogram, and area of parallelogram is equal to the size of my RT cross RT plus dt minus RT. So again, let me draw larger. If this is my RT, this is my RT plus dt, this vector here is RT plus dt minus RT. So the area of my triangle is half of the size of this vector cross this vector. Great. So my increase in area is dA is equal to the size of RT cross R of t plus dt minus RT. But what is this quantity RT? So what is this R of t plus dt minus RT? So recall that R prime of t is defined as the limit of dt going to 0 of R of t plus dt minus RT over dt. And therefore my quantity here is just going to be R prime of t times dt. Therefore dA is the size of RT cross R prime of t dt. And dividing by dt on both sides, I get dA dt is just going to be the size of RT cross R prime t. So this is just the size of R cross V, where V is my velocity. But in our first problem of this discussion, we showed that in such a scenario, R cross V is constant because this is my angular momentum and it's conserved. And this is constant by problem 1. Therefore, dA of dt is equal to the size of RT cross VT, but this is the same for all t, so let's just plug in 0. This is the size of the cross product between R of 0 times V of 0. And what is R of 0? If we plug in 0 to our equation here, it's going to be R1, 0, 0. And my V of 0 is R prime of 0. And what is R prime? This is negative R1 omega sine omega t, R2 omega cosine omega t, and 0. Evaluate at t equals 0, we get this is 0, R2 omega, 0. And therefore, R of 0 cross V of 0 is the determinant of ijk R1, 0, 0, 0, R2, omega 0. This is going to be just k times the determinant of R1, 0, 0, R2, omega. This is equal to 0, 0, R1, R2, omega. And therefore the size of R0, 0 cross V0 is the size of this vector, which is just R1, R2, omega. And this is also equal to our dA dt.